All right, welcome back. Today, we are going to get into the weeds on something that is, quite literally, the gateway to our digital world, SSH, the secure shell. I mean, this is the protocol that lets us securely manage pretty much everything, from tiny little web servers to absolutely massive cloud infrastructures. But as you're about to see, that security is under constant, and I mean constant attack. Let's get into it. Think about it. Every single time you type this command, you're essentially opening a door to a remote system. And you're putting a whole lot of trust in that connection, right? You trust that the lock is secure, and more importantly, that you're actually talking to the right server. Today, we're going to pull back the curtain and see what happens when that trust gets completely shattered by some seriously sophisticated attacks. Okay, first up, we have the classic, the oldest trick in the book, the brute force attack. The best way to picture this is an army just endlessly, relentlessly battering the front door of your digital fortress. They are trying every single possible key combination over and over and over until one just clicks. It's loud, it's messy, and believe me, it is happening all the time. And the scale of this is, well, it's kind of hard to wrap your head around. Modern botnets, using incredibly fast tools, can scan the entire IPv4 internet. We're talking over 4 billion addresses, looking for open SSH ports in less than an hour. So let that sink in. If you have an SSH server anywhere on the internet, it's not a question of if it'll be found by attackers, it's a question of when. And the answer is probably in the next hour. So how in the world do you defend that front door? Well, you have to think in layers. Look, having a strong, complicated password, that's a decent start, it's good. But at the end of the day, it's still just a key that someone could eventually guess. What's way better is using public key authentication. With this, you're not using a password at all. You're using a cryptographic key pair that is so complex it's virtually impossible to guess. But the best defense, that's rate limiting with tools like fail2ban. This is like having a guard at the door who sees someone fumbling with the lock and after a few bad tries, just boots them out and blocks them entirely. It stops the attack before it can ever succeed. Now let's pivot to something way, way sneakier. If brute force is that army battering the gate, a man-in-the-middle attack is more like a spy intercepting your messages on the road. This spy can perfectly forge the king's seal, tricking you into thinking you're talking to an ally when you're really handing all your secrets over to the enemy. It's all about impersonation. The main thing that's supposed to prevent this is the SSH fingerprint. You've probably seen it before. It's this unique string of characters that acts like a digital signature for the server. The very first time you connect, your computer saves this fingerprint. Then, for every connection after that, it checks to make sure the fingerprint still matches. This whole system is based on a principle called trust on first use. And the critical weakness, well, it's right there in the name. It just assumes that your very first connection is totally secure. But what if it isn't? And this is exactly how that classic attack works. You go to connect to your server. An attacker, somewhere in the middle, intercepts that request. They block you from reaching the real server and instead present you with their own fake fingerprint. Now, if you, the user, just shrug and accept that new fingerprint, well, it's game over. The attacker now sits completely undetected in the middle of your connection, watching everything you do, reading your passwords, stealing your data, and you are none the wiser. And, of course, these attacks just keep getting smarter. The Terrapin attack, which was found in late 2023, is a much more sophisticated version of this. It doesn't just try to trick you, the user. It actually tricks the SSH protocol itself. By messing with the sequence numbers during that initial handshake, it can actually break the integrity of the connection and force both your machine and the server to downgrade to weaker, more vulnerable encryption. It's a fundamental attack on the protocol's trust. Now we need to talk about what might be the most chilling threat of all. We've talked about attackers at the gate and spies on the road, but what happens when the traitor has been inside the castle the whole time? Someone who spent years earning your trust, all while quietly building a secret passage straight into the throne room. That right there is the story of the XZ backdoor. You see, this wasn't some quick hack. This was a patient, multi-year social engineering masterpiece. A threat actor, using the fake name Jia Tan, slowly worked their way into the open source community for a really important data compression library called XZUtils. They submitted good code, they gained trust, and eventually they were given co-maintainer status. That gave them the power to merge their own malicious code directly into the official project that millions of systems rely on. And I really cannot overstate how bad this was. This backdoor was given a CVSS score, that's the industry standard for rating vulnerabilities, of 10.0 out of 10. A perfect 10. That means it's as critical as it gets. It's easy to exploit from anywhere in the world, it requires zero user interaction, and it gives the attacker complete and total control of the system. It is, without a doubt, the absolute worst-case scenario. So how did this brilliant, terrifying thing actually work? Well, because this compromised library was a dependency for other core system components, it got loaded into memory by the SSH server itself. The malicious code would then hijack a standard, legitimate encryption function. So when an attacker tried to connect with a very specially crafted public key, this hijacked function would intercept it, pull a hidden payload out of that key, and just execute it with full system privileges. No password, no key exchange, no authentication at all. Just trying to connect was enough to get owned. So that brings us to our final scenario. What happens after a system is compromised? Whether it's from a brute force attack or a backdoor like XE, once an attacker gets a foothold on just one machine in your network, how do they spread? Well, that's where tools like SSH Snake come into play. SSH Snake is basically a network administrator's worst nightmare. It's a self-spreading script. The moment it lands on a machine, it starts hunting. It scours the entire system for any private SSH keys it can get its hands on in user home directories, in bash history, literally anywhere. Then it uses those keys to try and log into other servers, copies itself over, and starts the whole process again, spreading like a virus through your network using the very connections you trust. And maybe the most devastating part is this. As it spreads, it's also building a map. It creates this detailed graph of your entire network from the inside, showing the attacker exactly how every single machine is connected and which systems they now completely control. It turns a single tiny breach into a complete network blueprint for the bad guys. Wow. Okay, so after seeing all of these different ways in, from brute force to supply chain attacks to self-spreading malware, what's the big takeaway? The main lesson here is that securing SSH isn't about finding one single magic bullet. It has to be a deep, multi-layered defense strategy. So here it is. This is your checklist for a properly hardened system. First, disable passwords completely and use public keys only. Second, use tools like fail2ban to stop those brute force attacks dead in their tracks. Third, keep your systems patched. That's how you protect against protocol-level stuff like Terrapin. Fourth, always, and I mean always, verify fingerprints from a trusted source to stop those man-in-the-middle attacks. And finally, you have to monitor your internal network for weird SSH activity. That's how you might catch something like SSH Snake before it's too late. And that really brings us to the final thought. We've seen today that your security is only ever as strong as its weakest link. That could be a simple password, an unpatched server, a developer who blindly trusts the fingerprint, or a compromised open source library you didn't even know you were using. So the question I'll leave you with is this. When you think about your own systems, your own infrastructure, which layer is your weakest? Thanks for tuning in.